Good, so I guess we're good to start. So before I tell you who I am or why I'm even here, everything I've learned from people like you and from the community. So I owe a great deal of thanks to pretty much everyone for all of my talents. But specifically, there's 3 people that I've worked with to get ready for Derbycon. One's a relatively new engineer to our group named Bray. He did an awesome job, and we have 2 interns. We have many interns, but 2 of them helped me out. Lamar and Cameron did an awesome job. Sometimes it's the harsh reality that there's a lot of client work that needs to go on, so these interns and new hires kind of get kicked into the deep end and asked to swim, and these guys have just taken off like Olympians, so it's something I just wanted to recognize them for. So I'm here to talk about static analysis, specifically static analysis for the reason of finding vulnerabilities and bugs in software. So it's common now that we use sort of advanced systems and means to find vulnerabilities, whether or not we're fuzzing, we're using genetic mutation to find new code paths to go down, or we're using symbolic and concolic analysis, and we're emulating, and we're doing all these really cool things. But what happens when all that stuff fails? Or what happens when you don't have enough processing power? You don't have a supercomputer in your home or your office to actually find these things. You need something to guide that research and put you down the right path to actually finding a vulnerability. So that's what this is about. So I'm John Twetteray. Set 4 is kind of what I go for in CTFs and stuff. A little bit about me. I'm a security researcher at the Patel Memorial Institute. I've been there for about 5 years, and prior I was the civilian United States Air Force malware reverse engineer. Missed that culture, missed those people a lot. It was a really great time working for the government. So kind of overview of what we're going to be talking about. There's 4 main kind of sections to this, and they're going to bleed together. There's a lot of like computer science-y mumbo jumbo that's going on in here, and they may sound like fancy words like ontology, but I'm going to talk about them and just kind of demystify them because they're really not that fancy when you break them down. So we're going to talk about the 2 major components that we rely on to do a lot of this research, the workflow and how we actually put stuff into the system and get things out of the system. We're going to talk about MLIL, SSA, AST, PHI. So there's a lot of like alphabet soup there. The ontology, which is going to allow us to represent our data or format relationships between our data, the relationships and inference rules that we can make, so we don't have to store hard-coded relationships between data. We can do it on the fly, which is really awesome. We're going to talk about like visualizing a vulnerable program, so I'll show you what one actually looks like, and we'll take a look at assembly code, so bear with me if you don't like x86. And then we're going to talk about orchestrating components. So put a bunch of code on GitHub just a minute ago called Paper Machete. Paper Machete is really just an orchestration framework for all the stuff that I'm talking about. I'd hate to come up here and talk about a bunch of stuff and then like give you guys nothing. So Paper Machete, when we were naming it, first of all, we need a cool name, something sharp, something you can hit stuff with. That sounds awesome. But it needs to be confusing, right? So like, one, you can think of a paper machete as like a machete that you swing at paper and it just annihilates the paper, right? But you can also interpret it as like a machete that's folded out of paper, like origami, and you swing it at anything and it falls apart. So don't blame me if it doesn't work, right? I mean, it's in the name. All right, so the 2 major components that we're working with are Binary Ninja, specifically the Binary Ninja Intermediate Language Suite, which is absolutely fantastic and a pleasure to work with, and we'll talk about why we chose that. And Kraken Knowledge Graph. So Kraken has a query language called Grackle. It's really cool to work with, especially since I'm not a data scientist. I've dabbled a little bit, probably enough to be dangerous, as they say. But Kraken has been really easy to kind of smooth into, right? I worked with Tinkerpop and Cypher and Neo4j and all that stuff, but Kraken has just been kind of intuitive as a kind of generic computer scientist. So the overall workflow that we see here is output step 1, we have a binary. It's represented as this gear, right? We throw it into Binary Ninja and we say, all right, disassemble this and give us the intermediate language representation. That means we can originate from x86, x86-64, ARM, MIPS, Thumb, whatever is actually supported as a lifter. And Binary Ninja lets you actually write your own lifters for your own architecture. So if you guys are doing embedded device VR and there's no lifter for yours, if you want to, you can write your own lifter and go to town with this. So that was really the aim, to sort of be multi-architecture. Binary Ninja gives us that. At that point, what we do is we look at every function and every basic block in that function, but once you drill down, you get to each instruction, and each instruction has an abstract syntax tree, or AST, that's representative of it. That's sort of like this tree on the far right on 3. We take all of that great detail and we throw it in and we map it to an ontology that we've developed. And that ontology is what Kraken uses to kind of help insert all the data into its database and kind of track all of it. And then on number 5, we ask our database stuff. We say, okay, are there any vulnerable patterns? Are there any indications that this software might be vulnerable at all? And it spits us out answers, and those answers turn into a shower of money over here on the right. I'm still working on part 6, so if anybody wants to help me with that, let me know. All right, so you might be thinking this sounds really familiar, right? It turns out this isn't really novel research because a really friggin' talented guy named Fabian Yamaguchi released a dissertation in 2015, I believe, for his PhD titled Pattern-Based Vulnerability Discovery. It's like 170 pages, and it's without a doubt my favorite PhD dissertation I've ever read. Believe it or not, I've read quite a few. So in my line of work, it's very common that we look at what people are advancing and doing in academia and try to apply it to real world problems. So this has been sort of like really, really inspirational to me. So I knew that when I started this, it was possible because of his efforts. So he released a tool called Yorn that basically focused on C and C++, and like he did everything from scratch. Like he's done so much more than this research, and it's amazing to see the entire progress to that. So Yorn is really cool. He actually left, once he graduated, I think he's at Shift Left now, which does sort of the same thing for Java code. And these same concepts were kind of rolled into something called Bjorn, and Bjorn is like the binary analysis version of this. From what I understand, it runs on Red Air 2's ESL language. So ESL is Evaluable Strings Intermediate Language, which is like a human-readable intermediate language. So you can take your target architecture ISA and lift it up into ESL, and then do all of your analysis on ESL. It was something that we felt with them kind of rolling this into a commercial product that we might not get the support that we need, so we kind of decided to roll our own instead of rely on the Octopus engine or framework and all that stuff. So just to give him a lot of credit here. All right, so BNIL actually has a lot of different layers of representations to work with. All in all, it's probably going to be up to 9. 8 and 9, the high-level IL and ILSSA are actually going to be planned. I don't know if they're actually on the roadmap yet, but they want to do it. So the lifted IL really isn't a target that we want to choose, and the reason is this is the bare bones IL that gets lifted right from the ISA. So if you're dealing with, Thumb 2 or something, and you want to write a lifter for, some architecture, you bring it into lifted IL, and that's what you start translating from. So if you wanted to create a lifter that transforms this into LLVM or VEX, you would start at the lifted IL stage, and you would use that for debugging. No one's ever going to sit in Binary Ninja, view lifted IL, and find vulnerabilities. That's just not what it's designed for. So the low-level IL and the medium-level ILs are important because at each stage you get different granularity of information. So at low-level IL you'll get a certain amount of information. At medium level it resolves like types and like stack usage and things like that. So we get kind of data for free, and that's what I'm looking for. I'm looking to do pass off a lot of the heavy lifting to other tools if possible, especially when they're this good. So there's a talk at Infiltrate this year, 2017, called Be a Binary Rockstar by Sophia, Peter, and Rusty. And it's online. You can just Google it, or there's a Vimeo link here. This talk will go over these ILs and kind of talk about Binary Ninja and that whole process and explain why it's different than like VEX and LLVM. So this is a really good talk to do. I didn't want to cover everything that they've already done a great job covering. All right, so probably a cardinal sin, right? I'm showing assembly here. This is x86-64, and I don't really care that you guys look at every individual instruction. What's important to note is we have things like move and push and sub and conditional branches and things. And there's 4 major basic blocks, and basic blocks are sections of code that are divided by a decision. And that decision is, do I jump to this part of code or another part of code? So those are really important to us. So it turns out in this particular function, which is deregister transactional memory clones, it's something that gets added in by GCC on Linux. We don't have to worry about what it does. Bottom line is there's 4 basic blocks and 14 instructions. When we lift this to medium level IL, we actually go down in the instruction count and makes it more simple to read. So this is the non-SSA form, and what I mean by that is there's, actually we'll talk about SSA in a second. So this is a little bit easier to read in the sense that it says RAX equals 7, right? There's no like move or any there. You don't need to know what is destination and source first, second, AT&T and Intel syntax. It's just intuitive, right? So there's a condition boundary that says, all right, so if 7 is less than E hex, go this route. If not, go the other route. That's intuitive. That makes sense. That's easy to parse. It's easy to understand. We're used to that type of infix notation. So SSA, the reason why we want to use this is that essentially as variables are assigned or tainted, we keep track of that transaction. So at first we may have RAX that's set to something, so that's RAX1. The next time something is moved into RAX, it becomes RAX2 and 3 and 4 and so on. When there's two potential paths from different basic blocks that can meet into one basic block, we have a decision. Is it RAX1 or did it come from RAX2? What is the new value of RAX3? We represent that with a phi function. And phi is basically, you have a conditional choice here. We don't really know what it is, but it could be any of these two, right? So let's illustrate this. At point A, we have RAX1, which is SSA variable. So this is the SSA form of MLIL. And at B, we have a decision where the new RAX value is assigned. But also, if you follow down this other path, which is from another RAX down into that same node, it's, at this point, if we're not running anything, we don't know what the conditions were to set this, so it could be anything. These are some of the problems that we have when we deal with static analysis, is we have to reason about what potentially could cause that. And this is why symbolic and symbolic analysis are really important, and solvers are important, because they can do taint analysis to get us what we need as an input to get to that point, right? So we have to reason about these, and this does a really awesome job at giving us specific targets that say, all right, we can come from these 2 points. So as I said before, Binary Ninja has a lot of support for different architectures. I don't know if it's changed. This is a chart that comes from their frequently asked questions page. Like the second answer or second question on there, you click on that, and you can click on these red links like the asterisks and like the Y's here on the bottom for 5502. And it'll bring you to the instruction set, and it'll tell you what's supported and what's not. So there are going to be times and cases where you try to throw a binary into this, and you'll get unimplemented. What the heck does that mean? It just means that they haven't implemented it into the lifter. So all of this stuff is essentially the bindings for this are all open source. So you can go and implement that yourself if you absolutely need it for your project. But for the most part, for just every normal binary that you're going to run into, for the most part, you're going to have support for what you need, right? Architectures are extremely complex, and most of the time, like people say, you only really need to learn like 5 instructions. You can read x86. That's probably true. But if you really want to master the architecture, it's almost like a lifelong journey. There's just tons and tons of instructions. All right, so we talked before about the abstract syntax tree, and the AST is a way of like breaking down individual instructions. So what I have here is an MLIL SSA instruction that looks insanely intimidating. And the reason why I'm using it is because it's actually not that intimidating. What we're going to do is we're going to write an AST for it or show it. So at the very top, what we notice is that there's a left-hand side and a right-hand side of this instruction. And what this means is we're going to be setting RAX27, which is an SSA variable. So that gives us the set var SSA node. That has a source and a destination. I know you can't read what's inside of this circle node, but circle nodes are edge nodes. Those are like terminating nodes. In this case, all it says is var equals RAX, var equals 27, and size equals 64 for 64 bits. Then we have a 0 extension. So zx.q is 0 extend to a quad word. Then we have another 0 extension, which is 0 extension to a D word. And then we dereference memory. So we load from memory into an SSA from 2 SSA variables. The memory version is 7, so we actually watch tainted memory or memory at a certain address. So if we write to memory, we rev up the memory address, like kind of reference there. So that helps us too. And then when we go down, we see this. So if you go from the very bottom, you have 2 var SSAs, which is RDX27 and RDX26, and those combine into an add node. So we're going to add those together, and there's a load SSA. So we're going to load from memory at that location of value in memory version 7, and we're going to get that response or that answer. And then we're going to 0 extend it to a quad word, or D word, 0 extend it to a quad word, and then set of our SSA. So it actually going from the bottom all the way up to the top, it sort of makes sense. And there's actually a lot of information rolled up into here that we can ask the API about. These objects at various levels will tell us things like what might be on the stack at that point, or guess and try to resolve from instructions up above, down below, what an address or an instruction could be set as. It gives you flags, really nice things that we can rely on. And these are edge nodes, so source, destination, source, memory, all of this is defined in the actual API. It's not uncommon to see BNIL instructions that look like this, which look really complex, and they sort of are. Like when you're getting into parsing these things, it can be rough to understand how the AST looks. So Ryan Stortz, I think he's with Trail of Bits, wrote a really awesome plugin for Binary Ninja. You can just right-click on an instruction and hit View ILSS or the IL, and it'll show you all the representations of them, all broken out. It's fantastic. And Ryan, I'm sorry, I basically stole some of your AST parsing code for my project. Maybe I forgot to put your name in there somewhere. You can punch me at the next con. All right. So now let's move away from Binary Ninja for a second and talk about Kraken. So Kraken is really important because we get all of this gory information, and when you're talking about a function that could have thousands of subroutines with hundreds of thousands of function or instructions, and then you parse that into basically millions of nodes, how do you maintain all of this stuff and then all the state between them? It's a lot of data just for one single binary. And a lot of times when we're dealing with firmware, monolithic firmware images, these things are massive. So we got a way to actually store all this data. And a lot of times you'll hear this fancy term called ontology. And if you look up a definition for it, you'll see it's the branch of metaphysics that's dealing with the nature of being. Whoa. So that's too deep for this. Let me sip on my Red Bull here. Okay, way too deep. So if you look for another definition, we'll actually see it's a set of concepts and categories in a subject area or domain, very important, that shows their properties and relationships between them. So essentially what it's saying here is that if we think about something like baseball, okay, let's not talk about assembly and all this stuff at all. In baseball, there's a relationship between the players, right? So there's an entity called a player who sits out on the field, and he may be a first base player, a second base player, an outfielder, an infielder, and there's a relationship between those roles that they play. So for example, if there is a double play, the person on second base may tag a person out and then immediately throw to first. That's what you think about when you think of a double play, because that's the common case for that. So there's a relationship between the second player and the first player when a batter is hitting and hits to the second player, right? So those types of relationships can be defined in that domain or subject area in an ontology. So as we bring in data about our baseball players and about our field in this scenario, we can have Kraken map all of that data and kind of think about it as if it understands the game of baseball when it really doesn't, right? This is really, really important and insanely powerful. So that might be hard to read. I'm sorry. I stole this from Kraken's website. Essentially, when we describe an ontology, there's a certain set of concepts or things. And essentially, in the green here section, the second column, it's hard to read, but on the bottom it says person. At the top it says entity. So a person is an entity, right? And that person has things or traits to them, right? So it has a name, it has a weight, it has a height, right? So that thing is called a resource. That thing, that person can also play a role, like a wife or a husband. And that role is just something that they play, right? They can also play a batter or a pitcher, right? And then there's relationships that connect roles that people play together. So you might have a relation called team member, and that would connect a first baseman to a second baseman, which are roles that entities play, okay? And then there are rules. Rules are what allow us to do inference, and we're going to talk about that in a minute. But inference is also really important because you don't need to explicitly state that in the rule of a double play, that the two positions, out of all the positions on the field, are going to be the second baseman and the first baseman. But you can infer that from rules that you set, which means on the fly, we can gain intelligence about things. So I kind of already talked about this, so I'm going to kind of fly through these sections. An entity could be a person, a car, an assembly instruction in our case. A resource could be the age of a person, miles per gallon, or the source address of a memory dereference, for example. A role, basically a person in a marriage can play the role of a husband and a wife. And a car could be a sports car or a hybrid car, right? It gets a little bit more nebulous when you think about our use case, because an instruction can play the role of an in-basic block or contains operand. What the heck does that mean? Well, it's kind of arbitrary. We set these roles, we set these terms, so they're for us to decide. And what we're saying here is an instruction can play the role of basically belonging to a basic block or having an operand. That gives us two edge nodes or two roles to link to either the basic block that we're sitting in or the operands that are in us, right? So in ontology, the relationships, again, husband and wife could be linked by marriage, or a wife and a wife, or a husband and husband. Whatever we want to do to combine those two roles is something that we can get from this. I'm going to skip the next two, but basically that's the way that those relationships work. So here's Inference. This is an example I took from their site. I try to wrap it up into one that we use, but it's a little confusing, so instead I'll revert to theirs. So I'm going to ask you guys a question. I'd like some audience participation. This is the logic reasoning here. So a rule is what a concept that allows us to draw inference, right? So if I tell you 3 rules, 1, sheep only eat grass, okay? 2, vegetarians only eat things which are not animals. 3, grass is not an animal. What can we infer about this that's not explicitly stated? Yeah! Oh, yes! Yes, sheep are vegetarians. So that's extremely powerful, right? Like, when you guys are driving home today and that guy cuts you off and you call him an idiot, remember that that person is an insanely exceptional being. Our ability to reason about data around us and pull out things that are important from the world around us is so insanely powerful. And we've tried, the best minds that are out there have tried to simulate this type of behavior in computers and software, and it's been like failing consistently, right? We're getting better at it, but this is really, really powerful. This is what we're wired for. This is what we excel at. And to think that we can develop an ontology and a knowledge graph that can discern this information too is just like extremely exciting. Sorry, there was a weird sound behind me. All right. So in the sense of an ontology, we talked before about those SSA variables. So REX 0, 1, 2, 3. When we store that data, we don't have to actually make those edge nodes and say that these two are explicitly like connected. What we can do instead is just say, well, if we can write a rule that says, like, if it's an SSA variable and it has the same version name or the same name, getting really creeped out here, has the same. Thanks, man. Wow. Holy crap, this is really hot. I'm not joking. So I've heard, this is a premium malt beverage. So I heard that these were supposed to be hot. It is literally like they put them in a microwave. This is awful. Sorry. Oh, man, that is terrible. Yeah, that's what people said. All right, thank you. All right, so we have this, the name of the variable, RAX, and the version. So we can say, all right, if 2 variables have the same name but different versions, then we can link them together in an association. So we don't have to store all that stuff, which means when we're making searches, we don't have to search through all of these different extra things. We can do it on the fly. All right, so let's take a look at what a function looks like in Kraken. Here's the function that I'm going to be displaying, and this is the MLIL SSA form of the deregister transactional memory clones that we saw before. Just some junk that gets thrown in by GCC. The reason why I use it is because it's compact and it's easy to fit on one slide. Most instructions are really wild and kind of hard to fit on a slide. So this is it. Hopefully these colors show up okay. Basically, the top node at the top, I'll draw some lines here, is a function. So what we do is we go through a binary and we say, all right, give me all functions, okay? Then we say, go to one function, give me all basic blocks that you have, all right? And we'll tie all those together. The incoming node, or incoming edge, outgoing edge, and then all of the instructions in them are split out into like the purple blocks, which are either instructions, operations that are in those instructions, or values, which end up terminating into constants, variable SSAs, and then just plain old variables. So this is a single function that relates a lot of these different things. This is a lot of data when we start breaking it down, and if we zoom in to a specific basic block, the BB start and BB end are 9 on this blue node, which means this basic block only has one instruction in it. And then we can see that that instruction is, this smear knife ice is messing me up, man. It is, I feel like everything is like, I might be allergic to it. All right, if I pass. All right, so the instruction here is a jump. It's at IL index 9, and it links to a jump up, like instruction type, and then location of 0. So just kind of drilling into it. We have these generic edge nodes that are like in operand contains operand. We changed it to in node contains node. And then what we've done is wrap the edge name up into the block rather than having to rely on it in there. So the query language for Kraken is Grackle. It's really intuitive. So in this particular case, if we want to find all functions, we do match, which is a keyword that says, all right, we're going to go find something. In this case, we said $F. It could be $puppies. It's just whatever like variable you want it to be. And then there's another keyword called is a, and that's actually not 2 words, just is a, ISA. And then we say function. And that function type, or that name there, is actually mapped into our ontology. So we know what a function is because our ontology says what a function is. And then it returns all functions that are in this binary. We could do that in the console, and it returns a list of them instead of like a fancy graph of all of them. All right, so now we're at the point, let's go ahead and do some bug hunting. All right, there's a silly bug in the following code. I want to see if you guys can find it, okay? Don't worry, you don't really have to find it. And this is really kind of silly. So bottom line is what's going on here is it's asking a user for some input, and then what we're doing is going through it and making sure that the instructions or the characters that are passed into it are within ASCII range, and then it will copy that into another buffer and print out hello. Does anybody notice anything weird with this? It's a small nuance. So I'm going to go ahead and switch to the next slide, so I think I'm not giving you enough time. What's the value of length here? So it's actually undefined, right? And that's because at the very top on line 15, or it says in here, we have declared it, so we say uint len, but it never gets set anywhere. So what the heck does that mean? When we run this, does anybody know what might be just sitting in length? So it's a local variable, so it actually gets pulled from the stack. So as stack frames are collapsed and created, the program, like it won't zero that memory. It just stays whatever the heck it was. So next time you come into that range in another stack frame, it's just whatever's sitting at that slot. It could be anything. It may be 0, it may be 1, it may be whatever the heck. So that's really important here, is that this is a bug. This is an issue. And when we run this, most of the time you'll find that basically it just ends up printing hello and nothing else. And that's because it immediately finds a 0 and goes, okay, this is a 0 length string, and prints out nothing. But other times it'll crash, or other times it'll print out a lot of garbage. So that's something that we want to understand a little bit better. So I understand this isn't necessarily a vulnerability, but it's important because some bugs are vulnerabilities and some bugs are just silly bugs. But let's look at what this would look like in x86 64. So this is an image from Binary Ninja, just in normal assembly. So we have this memcopy here. This memcopy takes 3 parameters, right? And if we have to know that x86 64 uses essentially kind of like fast calling convention, where we load the register values in a specific order. So you have to know RDX is the first one, RSI is the second, RDX is the third, RCX is the fourth, and so on. So already the person who's viewing this, if they don't know that, they have no shot in hell in figuring out this bug, right? So once you understand that information, you can say, okay, well, RDI comes from RAX, and RAX up above, there's a load effective address at this location on the stack, which is considered var 48. Now I have to go back up my assembly chain all the way to the top of the function and find out where var 48 was actually set in the first place, if it's even set, well, at all, right? Should be. And then we go to the next one and say, okay, where's the pointer to our buffer where things are coming from? Oh, that's an RSI, so we go to RCX and figure out where that comes from, and then again, go up the chain finding where var 30 comes from. And we continue to do this really exhaustive process. What this actually looks like in Binary Ninja when we go to an intermediate language is we come down to that function, that memcopy, and we say, okay, well, it shows us, it says RDX version 7, RSI version 4, RDX version 11. There's this weird nuance with RCX. I can explain that later if you guys want to talk about it, but I'm going to ignore it for now. Basically, there should be 3 things passed to this memcopy. And we can see that RDX 11, just above, comes from a 0 extension to quad word from a var 34 0. Right? SSA is really powerful because it tells us when things are set. So if we declare a variable but never set it to anything, the first declaration is a 0, which means it's its infancy, that's just born. When it's set to something, it's actually like started at a 1. So let me go back to this code here. At the very top, we have a uint size equals 100. When we get that variable, it's going to be a version 1 because it's already been set. If we were to do the uint length turns that variable to a 0, and then later on, if we were to set that down in the code a little bit further, it would turn to a 1. So we can infer from this that we're passing into memcopy an uninitialized variable, right? This is really important. What does this look like in Grackle? So essentially, when we make a match, we say, all right, give me all calls that are, or give me all things that are instructions that have an operation type that contain the string call. Again, all of this stuff is mapped to our ontology, so we've defined what these are. We know from knowing the ontology how to ask questions of Kraken. So then we say, give me all parameters that are call SSAs. So now we have 2 big batches of stuff. In call, there's all this crap over here. And in params, there's all this crap over here. And if we think of a Venn diagram where there's like an overlapping between those two, the union is where we take the call and the parameters and say, all right, where are these two actually linked by something? And then we say, all right, out of all those var SSAs that we just did, give me ones that are version 0. So this means we have the union between all calls that contain parameters and all parameters that are call SSAs that are specifically version 0. So at the end of this, we have exactly what we're looking for. And when we run this, we get nothing. So why is that? The reason is because when we asked for this Kraken to reason about all of this and give us this information, we explicitly asked, are there any calls that contain parameters that are version 0? In this case, it didn't happen. There are none here that are version 0. But we can look and say that RDX really just comes from a version 0. So there's one level of indirection here. These are the types of challenges that we have to deal with because optimizing compilers and whatnot, like it's not just going to give you what you want. Doesn't mean that the last signature isn't valid. Maybe in some function or some program somewhere there is that case. So it's still valid to us. It just didn't work in this case. So we want to extend this a little bit. And we can go one further step up and get all this information, and eventually it'll actually return a chain. So this is kind of confusing, but at the top left, there's a purple blob, which is an instruction. On the top right, there's another purple blob, which is another instruction, and you could find a connection between the two through the var SSA 12 version 0, our RDX 12 version 0. So it turns out that this was something that happened earlier. That's supposed to be the same version here. Don't worry about it. They came from different versions of this binary. But what's cool is that we actually see the connection between those two, and that connection between the two is the indication that we're looking for. So what happens if there's 3 levels of indirection or 4? Well, we can write inference rules to help us with that case, so we don't have to write really crazy long graphical queries. All right, so this is all really cute, but what about real bugs, right? I want to test this on real stuff because I'm not here to find bugs in your silly little programs. Well, I get all my news on like Twitter. I follow a lot of like influential security researchers and stuff, and I think there's still a lot more that I need to follow. But as I'm kind of going through it, I see this post. So somebody makes a comment, data is easy to create. It is, right? It's all around us right now, but it's difficult to curate into a set that's usable. And they say that the major challenge, this is a major challenge for data science or any science that's using data at all. So someone else chimes in and says, yeah, this is really a big hurdle. My problem in security is not a needle in a haystack. It's actually getting a curated benchmark data set. So I want my ImageNet for IDS. Where is that? Where does that exist, right? So the reason why I really chimed onto this is the person who responded to this is Dan from Trail to Bits. And he says, yeah, actually, we're working on an effort to do this. DARPA created a program called the CyberGrand Challenge, and in that challenge, there was a system called Decree, and essentially it's a modified version of Linux that vulnerable programs run in. And they took these supercomputers by these really talented people, like people at UC Santa Barbara and For All Secure and all over the place, and they asked them, create an automated system on the supercomputer that can find these vulnerabilities and patch them, and they pit them together in a competition. And it was awesome. I drank lots of beer while I watched that competition. It was sweet. So that's the kind of stuff that I nerd out about. And what Trail of Bits decided to do is we'll take all the stuff that was created by these really talented people, these vulnerable programs, and let's port them to Linux. Let's port them to Mac OS. Let's port them to Windows so that people can use this data in their own research. So that has been insanely helpful here. So on Trail of Bits' GitHub page, they have the CB challenge binary, multi-OS. And if you drill down into this, there's a bunch of vulnerable programs that you can compile and use. So that's what we're using for our benchmarking testing set. So if you want to know whether or not any of this crap works at the end, run it against code that we know is vulnerable, test it out, and then we'll start bringing it into real-world cases, right? So here, I wanted to thank DARPA and everybody's tax dollars for making this program a reality. The cool thing about DARPA and the thing that I really kind of admire about this organization is if DARPA asks you for a question, like, hey, I have a problem, can you solve it? You never go to DARPA and say, yeah, here's exactly how I'm going to solve that problem. Because they believe that you don't understand their problem if you have a solution. That's how prolific and how hard the problems that they're asking you to solve are. They're essentially problems that most of us would laugh at and say, that's not possible. But people make it happen, right? And that's amazing. So in this performer group, what they've done is, if you look in the GitHub for this, Capricorn Security wrote a program called Fun. And Fun is a service that implements a simple text generator based on the Markov process. Blah, 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 whatever. I just know it's vulnerable. So it tells us here, go down a little bit further, and they all follow the same format. They'll actually tell us what the vulnerability is. So it says there's an array of strings in the data sections called words, and that binary fails to check the length of that array before it adds stuff to it. That's really important. So we can override the length of this array. But a normal fuzzer typically fails at this because the array length is like 13,000 elements. So your fuzzer may throw a couple things into it and be like, there's nothing here, right? So we have to go further, let's go deeper. So the general class of vulnerabilities is this leads to a buffer overflow. There's an array that's set up in a buffer, and we can override the edge, the end of that. And what's adjacent to that may be critical in us actually exploiting or gaining control over this program, right? So MITRE has, obviously, as we know, CVEs, right? So like Heartbleed, all these things that come out that have CVEs attached to them. They also maintain a list of CWEs, or common weaknesses and enumerations. And there's just a ton of them. But on number 788, it describes this particular vulnerability. And it says, accessing a memory location at the end of a buffer. So there are lots of things that could cause or lead to a buffer overflow. In this case, it is 788 which causes it. So it gives us a little bit of information on where to start. And in fact, all the code on GitHub and the patterns that we're matching against are modeled after CWEs. So you can go to our CWE 788 script, and that's what shows how to actually query a program for this particular vulnerability. So then they go on and tell you all the challenges and why this would be hard, and none of this stuff is really important except for these couple of lines. So it says that this particular problem is going to pose a challenge for typical fuzzing, right? So if I set up AFL and I throw it at this, or if I set up a peach model and write a peach pit and I say, okay, go fuzz, I might actually have a really hard problem finding this. It says that it's easy for symbolic execution, obviously if you have the right environment set up, but if you branch into symbolic analysis during the wrong paths, state explosion can be insane, and plus there might not actually be support for special instructions called SSE. So once you get down that path, you're kind of screwed. You need to have the right tool set, and you need to have the right compatibility. All right, so if we go into the source code for this, it's really easy to find the lines that are vulnerable and the lines that patch it, because you just search for this if-def called patched or patched_1. And what they end up doing is when you compile this, you set this flag, and it'll either patch in a piece of code that'll fix the vulnerability, or if you just don't define patched, it'll leave it out and the program is vulnerable. So it's really easy to find out what's going on here. So on line 436, we actually just keep iterating over the words array. And every time we find a slot that is not null, we increment I, and we keep going. So that means we're going to look for an empty spot at the end and try to add something to it. Unfortunately, in this case, once we get to the end, we never check to make sure that it's actually the size of the array or if we're over it. So the patch basically just says, if I is over the size of our actual words, the number of slots in that array, bail out. Don't write anything there, right? So it's a very easy patch. All right, so let's show what this looks like in our paper mache type stuff. Oh wow, a decent amount of time. All right, so right now I said before, I'm going to do match $f is a function, and it's going to return one function that I have in here. I only have one function. You can specify the entire binary or just individual functions if you want to do testing and don't want to wait for all the analysis to complete. So this is our function node. You can double click on this. And this is really cool. Kraken has this really nice interface for being able to kind of debug all of your relationships and data. This is awesome for about 10 seconds. And then what happens is you have stuff flying around and you're trying to click on it. It's no. And and I'll be walking to the printer and one of our interns is working on this, is going click, 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 click. I'm what is going on over here? It's Kraken is just messing with me. So thanks, Kraken guys, for making this. This is awesome. And then we can keep digging down into our data and seeing all of this stuff. And obviously this really helps us to make sure that when we do find an issue, if we want to test a query, what comes back, the relationships and nodes between those are actually kind of what we're looking for. So let me go ahead and clear this. What I'm going to show in a bunch of different things here is I'm going to blow away all the stuff in here. So I'm going to do, what's really nice about Kraken is we don't always work on internet connected machines. We'll work on isolated networks. So we've all been in that dependency hell where it's we pull something over, we have a mirrored repo, and then you add something, it's crap, I need 15 other things, and you go get those 15 other things, damn, those need like 300 other things. You're like, oh my God. What you can do with Kraken is the releases, you pull down in a zipped package, you unzip it, and then you just run Kraken start. That's it. As long as you have the JRE installed, that's it. That's huge. That saves me so much damn time. So I'm like so much more efficient. Like on my performance review this year, I'm going to say that I'm like 1,000 times more efficient. And hopefully my boss is watching. I need a big raise. So that's what's really cool about this. So what I'm going to do is type clean. Clean will stop everything, and then ask me if I want to blow away all the data. So I'm going to say yes in this case. All right. So I'm going to do is Kraken start. It's really important that we wait for this banner to print out. The banner printing out lets us know that the local server is running and it's ready to ingest data. If we start trying to interact with it or push data to it before that banner prints out, we'll have some weird issues. How's everybody doing? There we go. Sweet. All right, so this is what we can go locally to port 4567 and reload this. And let me have this nice little interface. All right, so now that we have a clear knowledge graph, what we're going to do is something I completely forgot. What is this? Okay, so in our tool set, one of the things we have is PM Analyze. PM Analyze, I'm basically doing under the hood what this fancy paper mache menu is going to do, or paper machete. So paper machete is going to allow us to do all this stuff for us, but in a sense, I'm just kind of showing what happens under the hood. So we say PM Analyze, and I point it to a binary, and I can give it an optional set of symbols or names. If everything is stripped, then you just give it whatever the name is. So usually it's like sub underscore or an actual hex address. And it'll go to those particular binaries, analyze those, and adjust them in a bracket and leave everything else alone. So for time, I'm going to do just this function. And we get some verbose output. And this output is the ISA for each one of those. You don't see this or interact this when you're using the paper machete. Basically, it just says, oh, there's an IL starting here, here it is, here's the size, it's this, and then ES and all that stuff is described in the source code. Basically, it's not important. Basically, what it means is we have a function or a file called fun.grackle, and that's ready now to ingest into Kraken. We're working on overhauling the entire migration piece. There was like a Pokemon example online for how to use this, and I was like, oh, sweet, I'll just use that. And what I did is, like, when I wrote this, we're like, okay, let's analyze the entire binary and just write all of our Grackle queries for all of our data into one big ass file, and just like throw that at Kraken. And the Kraken developers were like, no, don't do that. And I was like, well, damn, you're right, I feel stupid. And they're like, don't do that at all. We have a migration thing for that. So we're working on migration. It requires some like stubs and templates to make. We're more than halfway done. We'll push that hopefully this week. At any rate, what I'm going to do is say grackle.shf to point it to a file, and then we'll hit enter, and then we'll just kind of wait. So what'll happen is now it's actually, it copied the ontology that we have defined into this Grackle file, and all the other queries to put that data in. At the end, it spits out all those results that we don't care about. It basically just means everything worked. So at this point, what I'll go ahead and do is I'll run our paper machete. So I'm going to run all scripts, which what this does is looks into a directory called CWE Scripts, and it'll grab that and use the Python driver for paper machete or for Kraken and say, all right, does this signature exist in the knowledge graph? And it'll keep going down to each one. So right now we have a few example ones for you guys to work with, CWE 120, 121, 129, 134, and 788. And right now it came back, for some reason this is duplicated, I need to double check it. But it says CWE 788, array index missing bounds check at a certain location associated with a certain variable at a certain ID and all this stuff. So this is actually really nice. It actually told us where an issue might be. So let's copy that address and let's go into Binary Ninja, into the unpatched version that we brought in, and I'll go to that address. And it tells us this. So what does this mean? At this point, we still need to understand as a reverse engineer what's going on here, right? It's not like, boom, vulnerability, drop the mic, and I'm done. This is where we would say, all right, human reverse engineer who's either really expensive or has a lot of like projects that they have to work on, now you get to just focus on this one part. Tell me what's wrong here as opposed to the ocean of other instructions here. Or you can point your fuzzers at this location, or you can point your symbolic analysis or emulators or whatever. So what this tells us, if we look at this loop right here corresponds to this for loop on line 436. And what's happening, it's going through this array looking for null, and it's incrementing this counter by 1 every time, and that counter is I. So EDX1 version 2 is what's being incremented by 1 every time. That's our counter. and it's saying EDX36. So when we come back to this and it tells us EDX36 is an issue, there's no check on that to make sure that when we index into that array, that it's not within the bounds of the array. So that's like insanely important to notice here. So if we flip back to the known good states, right, it goes through this entire thing, counts up this variable as much as it can to an empty slot, and then right down here is where it'll start writing to that point. If we go to the patched one, what happens is we see that very same loop, but at the end of that, we have an if, and it says if that particular variable is over 11,999 and we index from 0, so meaning if that's larger than 12,000, which is the size of our words array, holy crap, don't write there, that's bad, and it bails out, right? So the vulnerability before was that's not there, so it just continues to write. So in that case, that actually found a real-world vulnerability. That's an issue for this particular case. So what's the end game? What are we looking to do with this? This is a really bold statement. Basically, I want no human interaction in this. And what I mean by that is, in order to get to this point, and this is one of Fabian's remarks in the opening remarks of his PhD dissertation, is he says, essentially to understand how we can train algorithms to find these particular patterns, we need to understand how we do it ourselves. Which means we need to write a lot of grapple queries, which means we need to hand jam a lot of stuff, and we need to see what works and what doesn't, and what catches certain things and what fails. And from that data, we can actually start to train algorithms that might be able to look for these things themselves, not generate necessarily Grackle queries, but look at Grackle's edge nodes and learn our ontology and learn what a binary looks like in medium-level ILSSA, and start to reason about the connections between them and say, hey, there's a problem here. You need to go check this out. So this is, again, an extremely bold statement. This is DARPA-level statement. This is not something that's easy to do. I don't know if I'll ever make it there. At this point, this is probably just going to become a hobby shop project for me. But what I really want is, I want this research to guide the big guns, and those big guns are those cyber reasoning systems. These are all of our efforts, and actually the big guns are you guys too. It's all of our researchers, the people are looking to make code more secure or looking to find capabilities. This is what I want out of this. And again, I want you to do something amazing with this. So all the research that we've done so far, it's on GitHub/set4/papermachete. You can download everything right now. We have a huge README that tells you all the issues and problems and things that we're going through. We're really transparent about like crap just not working at some points, or like false positives and things. We're at the early stages of this, and like I said, we're going to have hundreds of queries to write. Different versions that work in different things to understand exactly how a human works when they're finding these vulnerabilities. And only at that point is when we're really going to be successful. Thank you, guys.